In the previous mini lecture on Laplace transforms, miscellaneous Laplace transform theorems, we did the time scaling and the time shifting theorem. Now we're going to do the differentiation with respect to S. Okay, this particular theorem says the following. Suppose I have the Laplace transform of f of t. This is equal to f of s. Okay, now I'm going to take this Laplace transform of f of s, and I want to differentiate it with respect to s, d by ds of f of s. And the question is, what does that result in? And the answer is that it comes out to be minus the Laplace transform of t times f of t. In other words, when we differentiate by s, it's equivalent to finding the Laplace transform of t times whatever f of t we started with before. Okay, so the question is, how do we establish this? And the answer is the same way we do every other one, which is to say we will write down, first of all, the Laplace transform of f of t in its integral expression form 0 minus to infinity of f of t e to the minus st dt. And then we'll just differentiate this on both sides, d by ds of Laplace of f of t is then the same as d by ds of the integral 0 minus to infinity f of t e to the minus st dt. Okay, so because we do not have any, at this point we don't have any functions of s in our limits. Okay, these limits do not have functions of s. Because they don't have functions of s, we can take the d by ds right through the integral sign to the function of s. So let's go ahead and do that. This is equal to the integral from 0 minus to infinity of f of t. The only expression we have with s in is right here. So this is d by ds e to the minus st dt. And then this expression, we just take the derivative, minus infinity to infinity of f of t. The derivative of this is minus t e to the minus st dt. So then we can take out the minus sign, so we have minus the integral 0 minus to infinity of f of t times, well, let's put the t out over here in front as well. So this is minus st dt. So this whole thing is minus the Laplace transform of t f of t. Or we can put this the other way around, and then we can say that the Laplace transform of t f of t then is equal to minus d by ds of the Laplace transform of f of t. Okay, so let's just do one or two applications of this. So an example would be, say we're given Laplace transform of u of t. This is equal to 1 by s. So now we want to find the Laplace transform of t, u of t. So this is minus d by ds of Laplace transform of u of t, which is 1 by s. So this is minus 1 times minus 1 over s squared, which is 1 by s squared. If we want to find the Laplace transform of t squared u of t, then this is minus d by ds of the Laplace transform of tu of t. This is equal to minus d by ds of at 1 by s squared. Again, this is minus, and we'll just put this is minus 2 over s cubed, or 2 over s cubed. Okay, so anyway, you can see the applications of this is pretty nice. All right, now we're going to look at the final value theorem. The final value theorem says the following: if the limit as t goes to infinity of f of t exists, okay, if it exists, then we can find the final value that the limit of t as t goes to infinity of f of t is then equal to the limit as s, the limit as s goes to 0 of the Laplace of s times the Laplace transform of f of t. All right, so how we're going to prove this? Well, we prove it the same way we always do. We find some Laplace transform expression that we can use in a proof. In this particular case, we're going to have that s times f of s minus f at 0 minus this is equal to the Laplace transform of d by dt f of t. Now, why do we use this? Well, because if f of t has a final value, then at that point the derivative is going to be equal to 0. So that's the hint that we need that. So let's write the definition of the Laplace transform of df of dt. So we got Laplace here, the Laplace of d by dt f of t is equal to the integral 0 minus to infinity of d by dt f of t e to the minus st dt. Okay, so now we want to take the limit of this as s goes to 0. So the limit, let's put the limit as s goes to 0 of the Laplace of d by dt f of t. This is equal to 0 to infinity of d by dt f of t e to the 0 t, which is 1 dt. So this e to the minus 0 t becomes 1, and we have 0 minus to infinity of d by dt f of t dt. Okay, so this expression then just becomes f at infinity minus f at 0 minus. Okay, now, but on the other hand, the Laplace of d by dt f of t is just s f of s minus f of 0 minus. So the limit of that's as s goes to 0 of the Laplace of d by dt f of t is equal to the limit as s goes to 0 of s f of s minus f of 0 minus f of 0 minus, because this expression right here is just a constant. So its limit as s goes to 0 is just whatever it is. So now we have two expressions for the limit as s goes to 0 right here and right here, so we just put them together and we have the limit as s goes to 0 of s f of s minus f at 0 minus, this is the same as f infinity minus f at 0 minus. And so we just cancel out the two here, and we have that the limit as s goes to 0 of s times f of s, let's put here we have s times f of s, this is f infinity, and that is what we set out to prove. So we're done with this one. And now let's just do a couple of examples. Okay, first we'll just take the Laplace transform of, let's just use e to the minus at u of t. Okay, this is 1 over s plus a. So now we want the final value. So the final value will have the limit as s goes to 0 of s times f of s equals the limit as s goes to 0 of s over s plus a, which is equal to 0 over a equals 0. Okay, so this works just fine. Now let's take the Laplace transform of e to the at u of t. Okay, this turns out to be 1 over s minus a. Okay, so now if we look at this, what we'll see immediately that the limit, the real limit of e to the at ut as t goes to infinity, this is equal to infinity. That is, the limit does not exist. Okay, so if the limit doesn't exist, the theorem doesn't apply. But let's apply it anyway. So when we apply it, we'll have the limit, here the limit, as t goes to infinity, of L of e to the at u of t is equal to the limit as s goes to 0 of s over s minus a. And then when we do this, we're going to have 0 over minus a, and that's 0. Okay, so the idea here is that we can get completely, so we'll just say here that the result is just plain wrong. Just plain wrong. Okay, so we do not want to apply this limit. So the problem is, what's wrong here? And the answer is that 1 over s minus a has a pole on the right-hand plane. So here is, the pole is here. This is the real, this is imaginary. So this part here is the right-half plane. Okay, of the complex plane, of course. So if we have a Laplace transform expression that has a pole in the right-half plane, then we cannot apply the final value theorem for the simple reason that the final value doesn't exist. So we always have to be aware of this when we try to apply the final value theorem.